Okay, so this video is actually a correction on one of the videos, and you probably already saw the error on it. And clearly I was spaced here. I was mixing formulas up here, and that's, when you're recalling formulas and everything, sometimes it's a bad idea. And so I mixed some formulas up here. This is, if I can get my thing to scroll here. Stop this here. Why don't you scroll? Just a second. Okay, I know the screen just jumped on you, but this was an example where we did same figure, VTN 1 volt, VTP negative 1 kN, Kp equals 2.2 milliamps per volt squared, lambda p, lambda n. So I'm just this is the work that we have here, and we did part C first. Parts A and B we did correctly, but part C I made a mistake here. So first off, this is correct here, so let's go ahead and mark this. This is correct. This is correct. And then some of you maybe were screaming at me on the screen. This is wrong. Why is this wrong? Well, what I was saying is that GM is equal to IC over VT. Except, of course, this is for a bipolar device. And what do we have here? We have a MOSFET. We have a MOSFET device. And so this is wrong here, so I'm going to just erase this here. And we're going to put in the correct thing here in green. So the correct is that GM0 would be 2 square root of Kn times Iref, which would be 2 square root of where's K? 0.2 times 0.25, which if I do that, then I'm getting a very different number, much smaller number. We get, come on, 0.2 times 0.25 square root times 2, and you get 0.447 milliamps per volt. So a much smaller number. So then of course that makes this line wrong, because this is not correct. And so what I should have here instead is negative 0.447 milliamps per volt, and then erasing that, we would get 267 divided by 2 times 0.447 is we'd get a gain of negative 59.7. And that's actually important to understand here, because what this is illustrating is that, and I'm going to scroll all the way to the bottom here of my writing, so the gain is much smaller here, so let's scroll all the way to the bottom here. So that's fixing that error on that problem. But then again, notice for this other example we did, or that you will be looking at, we got a gain of negative 39.5. So this is the star I want to put out here. MOSFET active loads have much smaller gains than bipolar. Transistors. And that's one of that MOSFET. There's only one T in MOSFET. Or it's MOSFETs, that's what I was trying to say. That's important because we're wanting to have high gain for an op-amp, and as MOSFETs have much lower gain, we actually don't necessarily want to use MOSFETs for my gain stage. And sometimes some op-amps actually do a combination of MOSFETs or JFETs and bipolars, because they get the benefits of the MOSFETs, which have much higher input impedances, and then the benefits of the bipolars where they have much higher gain. So some of them, but a lot of them, because we can do with the bipolar, we can do that Darlington pair trick. We don't have to do that with MOSFETs because just by definition and the way they're built, they have high input impedance. So, but with the Darlington pair, we can get around that. So if you look at schematics for op amps, a lot of them are done with bipolar devices, and that's again because we need that high gain. So this is, to correct that mistake that you probably all noticed and were confused on what I was doing.